So now that we've reached orbitals, like in carbon, where we have multiple different orbitals that have the same energy, so thinking about our px, 2px, 2py, and 2pz orbitals, the energy is equal. So it's how do we know which of these orbitals we fill in first? So because our rule prior to this was that we said just fill in the lowest energy orbitals, and that's what we've been doing. These, by the way, these types of orbitals have the name. Orbitals where the energy is equal are said to be degenerate. So 2px, 2py, and 2pz are degenerate orbitals. You may see that language used in your textbook, and maybe in problems and things like that. So the question is, how do we put electrons into these orbitals if their energies are equal? So we introduced our first two rules, which are we just go to the lowest energy orbitals and put in 2 electrons per orbital, and that we can fit 2 electrons in each orbital. But now that we have these degenerate orbitals, these orbitals have the same energy, we need another rule. And our third rule is what's known as Hund's rule. Hund was a German physicist. This rule is named after him. And his rule is that we, let me make sure I have the language consistent here with what it has in your textbook. The lowest energy electron configuration is to have your electrons in lowest energy is to put electrons with put electrons in different orbitals if they're degenerate with the same value, with the same spin. So that's what we're seeing here with carbon. I got to drag it back down so you can see it. So we're seeing that when I went to the 2p orbitals, I put, it doesn't matter which way the spins are. I could have put 2 spin down electrons, it would be the same. But the electrons go, if this represents px and py and pz, my y looks like an x there, sorry. And you can't see it. All right, let me just, all right, px, py, and pz. We put in spin up electrons into px and py. It doesn't really matter which of these are which. So when we put in an additional electron, when we go to 7 electrons, as is the case with oxygen, or sorry, nitrogen. Nitrogen is next to carbon. So if we have 7 electrons, let me just come down and give myself some space down here. So 7 electrons, we're going to fill in the one, all right, give myself a bigger box here. 1s orbital with 2 electrons, the 2s orbital with 2 electrons, and then our 3 2p orbitals. We'll have 1 electron in each of those orbitals, and all of them will have the same spin. It could be spin up, it could be spin down. That part doesn't matter. And then once we have filled up 1 electron into each of the orbitals, then we start filling in the other electrons. So as we go to, so this is nitrogen here. Now we have oxygen with 8 electrons. We're going to have our 1s, our 2s, and 2p orbitals. These orbitals will be filled up because they're lower in energy. We'll put 1 electron into each of the 2p orbitals, and then our last electron will go into as the second electron in an additional 2p orbital. Now, one other thing that I'll mention here is one way we can simplify our writing out of these electron configurations. So like nitrogen, we could write this as 1s2, 2s2, 2p3. Oxygen then would have 2p4. Is that we can, all these electrons here that correspond to, on the periodic table, the noble gas that is before, that is sort of on the right-hand side, that's before we start filling in the next set of electrons. If we have a full shell, we can represent that by the symbol of that noble gas. So we could write this as helium, then with our 2s2, 2p3. This is and it doesn't change it very much for these elements, but as we get further down the periodic table, it saves us a lot of writing. And this also introduces the idea of the fact that we have sort of different roles of the electrons here. Our 1s electrons don't matter for the chemistry that happens with the atom. It doesn't matter for electrons being shared between molecules. So we call these the core electrons, and they essentially don't participate in chemical bonding and things like that. And these electrons in the next shell up, these in the n equals 2 shell, these are what are known as the valence electrons, or outer electrons. And so everything with a value of n equals 2, these are the electrons that matter for bonding and things like that. And we'll see that in the next coming chapters. So we have our core electrons, and we can represent those core electrons using what's called a noble gas configuration. Meaning we can take one of our elements that's on the far right side, whatever's the one just before the element that we're considering in the periodic table. So for example, we were looking at oxygen here. The one before it is helium, and so we can write that as the core of our electrons. And then include all of the valence electrons separately. So this is a way of doing a shorthand. Okay, so let's skip ahead a little bit in the periodic table. So we've looked at carbon, we've looked at nitrogen, we've looked at oxygen. I guess we can do our next couple, fluorine and neon. So fluorine, let's get our number here. We have 9 electrons. So our first 2 are going to be in that helium configuration. Then we'll have 2 electrons in 2s orbitals, not 1s. The 1s orbitals are already here in the helium. And we'll have 5 electrons in our 2p orbitals. If we draw this sort of in our box diagrams that we've been doing, our 2s, I'm going to ignore the core electrons, the 1s electrons. They're still there. But we'll just draw the valence electrons. We're going to fill in all but one of the electrons into the 2p orbitals. And then we get to 10 electrons. So this is fluorine over here. And our neon, in its electron configuration, is helium with 2s2 and 2p6. And this is going to be true for all of our noble gases on the right-hand side of the periodic table. These all have full filled shells, meaning that all of the possible spots we can put electrons are full. So we write our 2s orbital, it's full, and our 3 2p orbitals, we have to put 6 more electrons in there, and these are all full. Now, filled shells are very energetically favored, and this is the reason why noble gases don't react with other things and don't share their electrons. They're happy. They've already got a full shell, and most of the rest of the chemistry that happens is other elements sharing electrons to try and be like the noble gases. Electrons don't, of course, have feelings, or they're not people, but sometimes it's fun to think of them that way. Everyone else wants to be like the noble gases, and so they do whatever they need to do to try and get the right number of electrons to match up with the noble gases. Okay, so that is the basics for the first couple of rows of the periodic table. We'll take a look at maybe some things further down the periodic table in the next video.